Hello, warm welcome and very good afternoon from IRS Dehradun. We're running the 44th DLP program on mapping, modeling and monitoring of landslides and earthquakes. This will be the third lecture in this course. The topic of the course is landslide hazard zonation and debris flow modeling. So let us first see what are the key points, take-home points that we are going to learn from this particular lecture. Okay, before starting, I would like to get you introduced to the types of the landslides. What are those? So if I see, this classification has been given by Barnes 1974. If I go, there are two axes. If I go this way, so there are the material involved. It is rock, debris or earth, what type of material it is. And this axis, the vertical one, is the movement type. So if I, this two axis classification, if I follow, I can start with the rock falls, when rock chunks simply they are falling due to the influence of gravity. It can be debris fall, and obviously earth fall is slightly not that much common. Then there comes the topples. So the whole material along the discontinuous plane is going to topple down under the influence of gravity. Then there will be debris topple and earth topple. Next comes the slides as such. So slides can be rotational and can be translational. So both are quite common. In case of translational, we can see there are discontinuous planes, planes of weakness along which the material is coming down. And if the failure surface is a curved one, then it will be a rotational slide. So both these will constitute the group slide as such. There can be debris slide and earth slide. Next is spread, where the material is going to spread. It will be not as rigid as this top three category. Now, next will be your flow, where obviously down this axis, my water content will increase. So spread and flows, they contain sufficient amount of water. Flow is a mixture of basically rock chunks, soil and water. So there can be rock as such will not flow, but still it is there. Most important is debris flow. We'll learn a lot about this, modeling of this part. And the last one will be the complex. So we all know that big landslides, they cannot be of one single type described here. So that is a mixture of basically more than one type of landslide. So that is why they are complex. Maybe in the beginning at the source zone, the landslides are rock fall simply, and the end they have become earth flow or debris flow. So that is why they are complex. Before going to the core aspects of this lecture, I would like to get you introduced to these 4 or 5 important terms. What is a hazard, disaster, vulnerability, susceptibility and risk? Hazard is an event of occurrence that has a potential for causing injury to life and damage to property or the environment. I hope disaster and hazard, these definitions are quite common to you. Let us come to the vulnerability and susceptibility part. Vulnerability as such is the area determined by the capacity of its social, physical and economic structures to withstand and respond to hazard events. So vulnerability is always element specific. By element I mean it can be the total population, can be the cropland present there, can be the industries, can be the factories present. So they are all at stake. So that makes this vulnerability. Next is susceptibility. Susceptibility deals with all the elements who are susceptible. So which makes the area susceptible. Capacity of vulnerable elements to withstand an action of a given degree of severity, or it is the likelihood of occurrence of, suppose in case of landslides or the hazard in an area based on a local terrain condition. So susceptibility of a particular land piece because of, suppose due to a landslide or earthquake hazard, depends upon the rock type, the vicinity of that area with respect to a major fault system, a shear zone, or what is the soil type, soil erosion type, all these factors. So if I take this together, that gives me the susceptibility of that area. Vulnerability I have described is element specific. Now if I combine these two, I get a term called risk. So risk is basically it's a function of both susceptibility and vulnerability. There are other functions we're not going to discuss here today. Let us understand the landslide stage-wise. First stage will be the inventory making. We start any work on landslide with this inventory. Is just simply picking up the pixels or the area which are prone to landslide, where landslide has happened. So it's simply an assessment on or monitoring stage. Then there will be vulnerability, there will be susceptibility and risk, as we have seen in the previous slide. So all of them are mostly assessment. We are assessing the landslide. And then finally we'll come to the modeling aspect. So modeling aspect basically will tell about the mitigation. So how to mitigate the landslide. Well, I'll start with a particular example that we have done. We have modeled in Nepal, Sankosi landslide. So that happened in 2014. We have taken, like what we have shown in this table, pre-event data and post-event data. Pre-event data, we have taken February 27-13, and post-event there are temporal dataset, 2-3 datasets we have used. We have used mainly the LISFO and RESAT data. This is the RESAT to LISFO FCC image, false color composite image, on 12th September 2014. Now you can clearly see that how the image is will help you to detect the landslide zone. This is the actual landslide that has happened. How do I identify a landslide on a satellite image? First point will be this: look for this arc-weight shape. It is always will be of this kind or the other. An arc has to form, arc-weight shape. Then there will be tonal difference from the background to this, textural difference, others, and among others. Now please see, there is a river flowing this direction. If I ask you the direction of flow of the river, it's very easy to tell from this image, because reservoir has formed this side. So river obviously would have been coming like this. So this was the direction of the flow. Now landslide came here, the material, debris and all that blocked the river, and that is how we get a reservoir created in this site. Now if we know the scale of this photograph, the image, so obviously we can get to know what is the dimension of this landslide. Along with that, we can get to know the dimension of this lake, how much material, how much water it holds. That also is possible if we have a DEM. So that basically gives a three-dimensional view. So the depth is there, and width and your length is always there. So from this we can very easily tell that what will be the water accumulation in this reservoir. Now if I know the amount of water that has been stored here because of the blockade by the landslide, so if I breach this, if the landslide blockade gets suddenly breached by artificial method or natural method, suppose, then the whole water is going to come this side downstream, and this is one of the major rivers that basically brings is capable to bring floods in Indian part, that is the Kosi in Bihar part. So something happens here, it will directly affect the Kosi river, and Bihar gets flooded. So that is how we have seen that particularly in this case, in this landslide, what happened, the Nepal authority, they have blasted off the landslide material, but that was a controlled blasting. So slowly the water was allowed to go downstream. We have in this study have calculated that what is the time window that we have till we blast it off here and the water reaches Indian side. So what is the time available? So that is basically the evacuation time, becomes the evacuation time in case of a major flood event, potential flood event. Okay, this is another event that more closely we can see there's a tributary also contributing to this, and the material, landslide material completely blocks the flow of the river. Right, now we come to the hazard zonation part. This is the, I will start the hazard zonation with an example. This is what we have produced. NRC IRS, they have produced this hazard zonation map long back, and this is from the Kedarnath town and vicinity, Kedarnath town and adjoining areas. This is where Kedarnath city is, town was, and the river Mandakini flows like this. From Diden, you can see that the hazard classes, if you consider, there are very high to severe classes are already there. So this is an example of landslide hazard zonation, obviously at a particular scale. Now I will come to the slides where I'll describe how to make this landslide hazard zonation map, the classification schemes. How do we go about this? So the materials that you require to make this kind of hazard zonation map, let us come from the inventory type preparations. What is the inventory landslide, where landslide is present? So first thing I told you that you have to make an inventory of landslide. You need pre-post event images. It can be something available already on Google Earth platform, GUI images, or can be the IRS Cartosat1, list for other type of landslide type of data. From that you can very easily make a landslide inventory of your study area. So once you make this, you can come to vulnerability mapping. Vulnerability mapping is what I told you. It's about the calculation of the elements present in that study area. So the elements that are put to stake. What are the elements? It can be settlement, can be road, can be agricultural field, it can be anything that you think that is important there. So you can digitize over multispectral images or simple pan images and get one map from one elements: settlement map, road map, agricultural field map. So all these, if you stitch together, put together, you get what is called the vulnerability mapping. Now out of these also you feel that my road is maximum stake is more vulnerable, so you can simply weigh these and you can put more weight to road, suppose, or settlement, suppose human settlement, that becomes most important, so you can put maximum weight to this before amalgamation of these layers. So these three layers put together gets me the vulnerability map. Now coming to the susceptibility map, as I have told you, there are several classes, there are several factors rather, they make that area susceptible. So what are the susceptible factors? What we have jotted down here is slope aspect, relative relief, geology, then structure, then stream, then land use, land cover, and so on. So we have used suppose around from 2 to 12, around 10 layers, 10 12 layers. Now all these layers may not be required, or even more than these may be required. So that is site specific. It's quite possible that you are satisfied with top 3 or 4 layers. You think that they are the only factors that make the area susceptible. The rest we can ignore. Similarly, it is possible that even there can be more classes beyond these 10. So if you put these different maps, slope, aspect, relative relief, geology, structure, stream, one after another, and then if you add these layers in an image processing software, you get what is called susceptibility map. Here again, you can put weights according to your wishes or your field knowledge. Suppose slope, I think I believe that in that area is particularly important. I have seen that more than 50-degree slope, wherever it is, I get a landslide. So I put maximum weight to this. So that is how I get a susceptibility map. Now, susceptibility map and vulnerability map, if I put together, I get a risk map. I'll come to the calculation part in detail later. Now, next part will be the debris flow runout modeling. Here we take help of one particular model and one particular software, and we get what is called the topographic, we get what is called the release, the 4 physical parameters like your height, velocity, momentum, and pressure all along your runout. So that is what we're going to do. We're going to learn the last part of this lecture. Let's stick to the methodology section where we come up with an landslide inventory, then we make a susceptibility map, inventory map, and a risk map. So we start with this satellite imageries, and then we get landslide inventories. So portions where landslide, portions affected by the landslides. As for the susceptibility mapping, many calculation is involved. I do not want to take you to detail of this, but simply philosophically, if I have to discuss it, I'll go this way. That these are the different layers that we have taken for susceptibility calculation, susceptibility mapping calculation. So all these layers, if I put together, and there are several methods available in literature, how do I play with these layers? So these are the layers. Some of them you will get from satellite imagery, some of them from ancillary data, like for geology you can consult the geological map published by GSI. So from different sources you can bring this raster layers, and then you can put those together. You can play with this, you can stitch these layers by different methods. It can be statistical method, can be knowledge based method. Then putting them together is what is called your factor maps. So factor maps means this map is suppose a map for soil. Next layer suppose is for your slope. Then you get geology. Then you get structure like this. So these would be called factor maps. You can simply put still weight to these layers. So you think one particular layer is important. How do I get these factor maps? I have got these raster layers ready with me from different sources available. Now, if I juxtapose these layers over my inventory, so that's why first I prepare the inventory. If I juxtapose each of these layers with inventory, if I cross these two, I get a factor map. So suppose I cross slope layer. Slope layer will have this thematic layer will have several classes. Suppose I get 4 classes, 0 to 20 degree, 20 to 40, 40 to 60, 60 to 90, like this. 4 classes. You can see the distribution on this raster map. Now, if I juxtapose, if I cross this with inventory, landslide inventory, so I can easily see which are the pixels, that in the slope class that contains maximum landslides. So the inventory is going to give me the landslide pixels. I can simply see, okay, the 40 to 60 degree class in this thematic layer contains maximum landslide pixels. So obviously from there we can make out that the 40 to 60 class has some influence on occurrence of landslides. Like this we prepare for other raster layers also. Each of this layer we simply cross that with inventory, landslide inventory. So that gets me these factored maps. So once you prepare the factor maps, still you can put some weights, and finally you get a susceptibility map. So this susceptibility map, and if you remember, I have taken 3 elements, so built up, road and agriculture. If I put this together, I get a vulnerability map. If I cross these two, I'm not considering other factors for risk. If I cross simply these two, then I get a risk map. Right. In detail, the stages. So here is a landslide inventory map. You can clearly see these are the pixels, these yellow colored pixels, where the areas where a landslide is there. So like this, you can prepare your inventory map. Same inventory map, we have draped it over a cartosat image just to show how in 3D it looks like. So the Ukhimat town is before Kedarnath. The town is there towards your Kedarnath shrine. So the Ukhimat village, it has been affected by the landslide since long, 1998, then 2012. There has been reactivation of landslides on this slope. This side is Guptkasi. This slope is more vulnerable. So I can see I have shown the this red polygons. They indicate the active landslide zones. Coming to the vulnerability calculation, there are different building damages I have taken. So building footprint is what we take. We digitize those footprints and see how it has been affected. So building damage, then road damage. What are the roads that has got damaged, or that there's a potentially that it can get damaged in case of landslide. In hilly areas, I would like to tell you that if one lands, because hilly areas roads will occur, will go like this, and then it will go like this. So one single road can be punctured, can be affected by this one particular landslide, several locations. So that is what we have to look for. This is one single road only. Agricultural land, similarly, where the agriculture crop land has been affected, and where debris are lying because of the landslide, this you can do pre-landslide, potential areas where the landslides may fall, or post also. So if I take these two, settlement, road, and agricultural land. So agricultural land will look like this. These are lands present, they're at stake. Roads present, they are the roads, and they are the settlements, towns, villages, etc. If I stitch this together, I get a vulnerability map like this, where I have classified this into 5 classes. So very high is where the elements are at maximum vulnerable location. So from this we can make out simply that roads are something that we have given maximum weight, because roads are getting my red color. So obviously it's quite common that roads, I think in this particular case, is most vulnerable. It may be or may not be. It depends upon the operator's wish. So this is what a vulnerability map looks like. Now the susceptibility mapping, for this I have suppose taken 12 layers from geomorphology till soil erosion, different layers. In your study area, you have to see that the same size, same size of the study area you have to maintain. Then only you can cross it. So geomorphology, stream, faults, relinement, land use, land cover, geology, all these layers putting together. How do I put it together? First, each of these layers, so they'll be called one thematic layers, and in this thematic layer these are the classes. So geology, suppose 4 and 3, 7 rock types are there, so 7 classes are there. So these 7 classes makes my geology thematic layer. Now each of these thematic layer is to be crossed with first the inventory map. That gives me the factor map. This is one statistical example of to calculation of susceptibility. So the information value is a product that that we get out of this when we calculate the factor maps. The positive values indicate that that particular class in that particular thematic layer has more influence compared to the negative value or 0 values. So all classes you can see there. All thematic layer, all classes. Some of the classes in some of the thematic layers shows me very high values. So that indicates that they must be more influential as far as landslide occurrence is concerned. Now, if I put that together, the factor maps, all factor image maps, and then the landslide susceptibility map is something will look like this. So the red zones, again, I have classified into 5 classes. Very high zone are this. You can remember few slides back, we have shown that Ukimat town, there were many landslides. Please see the Ukimat town, this slope is coming under very high zone. So there is a kind of validation. You don't have to go to field. Obviously, remote sensing has some limitations. You have to be there in the field and check your data, check your output. But from this image also you can check, had these landslide polygons, or had this area not been covered under very high zone, there must have been some problem, some errors in your calculation. But here you can clearly see we have physically seen landslide occurrences here. At the same time, from my statistical calculation, the area is coming under very high susceptible zone. Now, so agriculture, built up, and road gives you vulnerability map. So vulnerable areas crossed with susceptibility gives me risk. There are other factors like factor of safety and socioeconomic factor that also is to be integrated in calculation of risk. But as of now, we're not considering those. So my risk here in this example simply means that we have considered the susceptibility and the vulnerability. So you can look for areas, look for pixels where because each of these pixel, what does it contain? It contains a susceptibility value and a vulnerability element, vulnerability value. So each of these pixels. So there can be vulnerability 0, susceptibility 100 conditions to susceptibility 0, vulnerability 100 conditions, and in between. So each of the pixel will tell you the susceptibility as well as the vulnerability of that pixel. Like side by side, you can see it will look like this. You can look for areas. You can look for areas where risk is high because of vulnerability high. Or again, similarly, you can look for areas where risk is high because susceptibility high. Okay. So that example was mainly from Mukhimat town, close to Kedarnath. We have done this kind of exercises for several other areas also. This is something from Jamunatri area. At this scale, we have Jamunatri shrine, and then we have prepared the vulnerability zone of this. This is post Kedarnath, I mean post 2013 flood event. Vulnerability, susceptibility, and risk map of Kedarnath area post disaster map. So again, I started this discussion showing you a map, classified map prepared by NRSC IRS long back. I told you that then also there are high zones, I mean high vulnerable zones were in the very close proximity of Kedarnath town. What we have, we can produce after Kedarnath 2013 event, we see that the town is really, it was vulnerable, and this is a post-dated validation, and we have seen that this whole Kedarnath town is surrounded only by very high susceptible zones. Like, so the first part we have covered half an hour, and we have covered the first part of this lecture, that was the hazard zonation. We have learned from this half, what we have learned is that we have learned how to prepare a hazard zonation map, what is susceptibility, what is vulnerability, what is risk, right? The next part is dedicated to the calculation, the detection of debris flow and their modeling aspect. In the beginning, if you remember, we have classified, we have given a classification where we have shown that there are some stages involved in landslide. Some are assessment, some are mitigation. So debris flow modeling is completely dedicated to mitigation aspect. What are debris flow? If you remember the very first slide where we have discussed about the type of landslides, so debris flow was coming under the flow category of the debris material. So what it exactly is, it is a fast moving liquefied landslide. So it's a fast moving one, and liquefied means it contains a lot of water. It's a mixed and unconsolidated water and debris basically. What debris is, it's nothing but soil, unconsolidated soil, rock chunks, etc. Appearance of this will be like a flowing concrete. Flowing concrete, and then the shape of most of the flow will be like a torrent. It's like a sharp crested trough, drain-like feature. So along that, the material has to come down under the influence of the gravity. Triggering mechanism for debris flow, like other landslide classes, also can be cloud burst, can be earthquakes, can be reservoir drawdown, among other factors. So if I draw a cross section of this profile of a typical debris flow, there will be a zone of depletion where from the material is coming, and there will be a zone of transportation. The material is being dragged down due to the influence of gravity, and there will be a zone of accumulation. And there lies, suppose, a river here. So this will be the zone of accumulation, this will be the zone of depletion, and zone of transportation. Along this slope, obviously there will be slope breaks, there will be platforms, so where the material also may get partially deposited. And if some typical slopes like this exist and it's coming with sufficient momentum, it's possible that the material, the amount of the debris will increase with the zone of with the increase in length of zone of transportation, because more and more material, because of erosion, it can contribute to my original debris flow. Now Reading has defined the debris flow like this. Famous sedimentologist, he has defined it like this. Debris flow are plastic flows. They are plastic flows in which sediment and water are fully mixed, and the original bedding or lamination, what is present in that rock, that are largely destroyed, that cannot be recognized now. Now, why the study of debris flow is important? It is important because you have to think about where exactly we are located. We are very close to the Himalayan thrust system. We are very close to MBT, and the active MCT and beyond also is not far from this place. So every now and then there are activation of seismic waves that keeps on making the landslides active. Then why to model a flow? So debris flow as such, by definition we have understood by now, But why do I model a flow? We have to model a flow because the first half of the presentation we have learned that the hazard zonation, how it has to be prepared. Now evolution of research on landslide has gone much beyond that. So now everybody is talking about mitigation. How do I mitigate the slide? So it's so the modeling of the flows can get you the outputs, required outputs. And obviously if you are doing the modeling by numerical methods, there lies the magic. Because its numerical is linked to the objective outputs. So anybody working in, suppose in Uttarakhand and in Dehradun and working in somewhere else in the world, well, if they use the same numerical method, they're supposed to get the same output. The same is not true for hazard zonation. So that is why that is subjective, and this particular method is very much objective. It's simply playing with the mathematics. Simulation of natural events of national importance has become very important. Honorable Prime Minister's 10-point agenda also in this regard very clearly say what is the importance of modeling all hazard all landslides, important landslides, big landslides. It can simultaneously tell you the causative factor. What are the causative factors of that? Then there is the most important part, future potential flow. We have seen one landslide to happen. What is the future of this? It can get reactivated. If it, then what should be the run-out zone in future? How much more material is supposed to come, and where exactly it is supposed to fall, and what will be its effect? Then the last point is that it obviously helps the hazard zonation, hazard mitigation measures. We have used here a RAM software, that is rapid mass movement software that we have purchased from the WSL Institute of Snow and Avalanche in Switzerland, and so the algorithm has been developed by them. What are the models that we have produced till date using the RAM software is, I have jotted down 5, but there are more. All these results are published in a recent Springer book. If it is searched by the author name, that is my name, and Springer, you'll get the results, detailed results of that here. Event 1 is Ukimat, event 2 is Varunavat Parbat Uttarkasi, event 3 Kedarnath. Then we thought that why not to try this landslide model has a numerical simulation outside Himalayan zone also. So we took one landslide from Malin in Maharashtra, Sahyadri Hills in Deccan Basalt. So it's altogether different from this. And then we have taken one from the Sankosi one, that is in Nepal. What exactly it gives us? It gives the height, velocity, momentum, and pressure, these 4 physical parameters along a slope. Then the estimation of real cause of widespread devastation, and it doesn't stop here. So we have provided a height, velocity, momentum, and pressure. It doesn't stop here. You can simply validate your results. So whatever result is coming here, that can be validated instrumentally in labs. Now we take another example in Ukimat. This is the town Ukimat, the village Mangli and the village Chunni here. There is a Ukimat Gram Sabha, falls under Ukimat Gram Sabha. Now this is the zone of influence. Landslide starts from this. These are the zone of depletion, transportation, and deposition. Similarly, we have taken one in Uttarkasi. There's a famous Varunavat Parbat landslide, and there's a trifurcation of this landslide that we have that's clearly visible from this LIS image and the Google Earth image. So from this LIS image, we can clearly see that the trifurcations are there in that particular landslide. How do I model this landslide? The physics behind this is to be understood very clearly. So what does the software do? Software basically takes some inputs. What are those inputs? They are DEMs. There are some maps. So the maps will be used to get a glimpse of where exactly the landslide is occurring. What is the dimension of that physical dimension? Digital elevation model will give you the depth parameter. So that this auto-rectified image and topo maps will help you to get the dimension, XY dimension. This will be giving you the Z value. So together this gives you the volume. Then the block release or the release area that you can simply mark on your satellite image. Release height you can put, and then there are some factors, geoengineering factors, frictional parameters that you have to give. So friction is something that basically doesn't allow the flow to happen. So this is my weight, suppose mg. So the mg sine theta is the force that is bringing the material red block down. So red block is my rock chunk that has to slide down. So mg sine theta, opposing this mg sine theta will be my frictional forces. So that will oppose. If mg sine theta is greater than equal to, even equal to friction force, so this equation, then your landslide is supposed to happen. Until your friction, that is S, total friction S, is more, so it will cling to its position. It will not slide. Now, how do I calculate this mg sine theta? Mg sine theta is theta angle, so that will be taken, that will be considered by the software from the DEM that you have given. Mg mass is, or the volume will be taken care from these two. Now, how do I calculate the S, total S, that is the total friction? Total friction, as because this is a debris, so it consists of two main classes. One is rock, the solid material, another is water material. So this is the friction due to the solid material, rocks, and this is the friction due to water material. We have to calculate the friction parameters, friction forces given by both these phases separately. So it's simply, this is the frictional coefficient, tan phi, then rho is the density, height, and cos phi, phi is the angle. This theta and phi are same. Then for your liquid phase is again rho, g, and u is initial velocity. In case of big landslides, it may happen that the source area is quite big. So the upslope, maximum upslope point, when it reaches the downmost point within this source area, so obviously it will gain some kind of velocity. So that is your initial velocity, or u. And then your xi. Xi is nothing but the viscous turbulent frictional coefficient. All these parameters except mu and xi will be taken care by the software itself. If you provide the software this kind of information. So mu and xi are something that the operator has to provide. Now, how do I know the mu and xi? There are frictional coefficients of different materials in standard charts literature available. So one can simply refer to that. If the equation is satisfied, if everything falls in proper place, then there will be simulation created. In 3D, we can see how the material is flowing. So the outputs will be like the depositional height, the velocity, the pressure, and the momentum all along the runway, runout. And there will be some profiles also that you can prepare, you can make from this. How the results will look like. So this is what the zone of initiation. Then the material is going to come down, and after the entrainment zone, it will be deposited here. The typical unchannelized debris flow will look like this. It is a torrent. So the river Chunni used to exist here only, and you can see this only single solitary house that is remaining there. The material came like this, and the whole village. There was a village here, and it is said that some of the skeletons, the people died. Some of the skeletons could not be recovered even till then. So the material is coming like this, and this is how the whole scenario will look like, all flooded by debris material. The result will look like this. So there comes your source zone, material flows like this. There's a trifurcation. This island, it is not affected, will not get affected by the debris flow. There's a channel like this, it comes, joins, and finally it deposits here. See the color bar, it shows you the velocity in meter per second. So at each point, if you click here, at each point, you're supposed to get the meter per second velocity. Similarly here, you can get the height information. At each point, suppose the road is coming. Can you see the road here? The road goes like this, and then it comes like this, one single road only. Now, the same landslide has affected this road at 1, 2, 3 places. Now, at each of these 3 places, if you can get to know the height because of the flowing landslide, you can think of putting a wall kind of structure, a dam kind of thing that will at least digest the initial thrust of the landslide, of the debris flow. So maybe it can arrest the road from getting blocked. Now, what do I do with this height information? If I can get to know that at this point the height is available is around 3 meters. So obviously at this point the material that will come is of 3 meter height. So immediately before this, if I put a dam, so dam has to be more than 3 meter height. That is the beauty of this. So that is how it helps the real mitigation measures. So if I put a dam of 3 meter, if I know that 3 meter is going to come debris, so more than 3 meter, 4 or 5 meter dam suppose we put here, so obviously that will be able the material will not be able to come at least onto the road. It can be saved. You can see two villages, the Mangli and Chuni in red, the circles. How the material has flown, and the color bars will detect you the height and velocity. Similarly, in profiles also, if it is the source area 0 to this 1 kilometer, it has traveled, the landslide has traveled, debris flow has traveled 1 kilometer. At each point, you can get to know the height and the velocity parameters. Similarly, we can get to know the momentum and pressure. You'll appreciate to know that momentum, why momentum is required, because height at times is not sufficient. So the material, the mass that is coming, which velocity, a particular velocity is important, because the suppose for a 3 meter debris height, I have implanted, I'm thinking of implanting a dam of 5 meter, but that 5 meter, will it be stable? We have to calculate, I have to see the momentum aspects also. With what momentum the material is coming. If the momentum is sufficient enough, then the 5 meter wall also may fall, may topple. So the momentum is something that you have to calculate. From this momentum, you can get to know that what should be the width of this dam, check dam. So obviously more width of the dam, height is 5 meter, that is okay. But if the width is more, then it has more power, more strength to withstand the flow of the debris. So similarly, pressure also, at what location, at these locations, suppose at a particular village, before striking this particular village, the pressure available to debris flow, to this particular debris flow will be this much. The momentum will be this much, the height and velocity will be this. So if these 4 parameters are known, then it's very easy to help to mitigate. It can be done before a landslide, debris flow has happened, or after also assessment can be done. This is what the trifurcation has happened in Bornaboth landslide, I have told you, and then the landslide, the model, debris flow model will look like this. So there is also a trifurcation of this model. If the model doesn't holds good, it's not correct. If it is not correct, from the source zone, it will not follow the exact 3 trifurcations, the 3 branches, as we have seen in satellite image. This is a post data analysis that we have done. We have selected only this area and other inputs that we have given, and from this we have seen that the material, the debris flow, really follows these 3 trifurcations, 3 branches. If it doesn't flow, if it goes elsewhere, then I have to tell that there is something wrong in my model. Similarly, all 4 parameters for this also can be calculated. One study we have done from Kedarnath event. Kedarnath is a major flood event that happened in 2013, and then and thousands, the casualty were there. Officially around 5,000-6,000 the casualty was there. If you see in several literatures it has been postulated what is the reason behind this. Some says that it's the sudden availability of water, so that basically gushed through this and then flooded the whole area. Rainfall, some people tell, some scientists tell that rainfall is the main contributor. Some tell that no, there is upstream, there is a Chorabari Tal, a lake-like thing, and then that breached on that very day, 15-16 June, and that is how the water availability to the this Kedarnath town was such that it flooded everything. From the remote sensing studies, we have tried to get what exactly happened in those, validated with ground truthing, etc. We found that from satellite images, it's very clear. You can see is immediately after the landslide happened, 21st June, and the event happened somewhere in 15-16 June. You can very clearly see these two big landslides. This is Kedarnath town. This is the town itself. And this is how the debris flow. Can you see the very big, long run out of the debris? And similarly, what one is there just down to that. So this, from this long debris flow, the material that accumulated, that came down and got accumulated here on that night or the next day, the water was sufficient, we believe, but it is not that much to flood the whole Kedarnath city. So whatever water was available, and that was flowing like this, and this debris is something that blocked the river. This part of the river is called Saraswati. That Saraswati becomes Mandakini downstream. So Saraswati was blocked, at least partially blocked, by this material that was brought by this debris flow. So it had to take another path that flowed exactly through the mid of this Kedarnath town. There used to exist a paleo channel here. So that paleo channel got activated, and the material that was blocked here had to take that least resistant path, that is the paleo channel, and the paleo channel unfortunately flows just at the mid of this, right across the heart of the town. So that is how the whole city has been devastated. This has been this result has been published in Natural Hazards Journal by our group. The DM will look like this. This is the Kedarnath temple, and this is how the flow 1 and flow 2 we can see on the DEM. DEM obviously we have projected on 2D. So this is the source area, this is the zone of influence. The zone of influence is something that we believe that these are the watershed divisions. Beyond this line, the flow, because of this particular, so from this particular zone will not go. So this is the zone of influence. So in this zone of influence, the software calculates and gives you all the 4 parameters. We have shown here the velocity, the height, and the momentum all along, and from debris flow 1 and flow 2. So total runout length in case of debris flow 1 was 1.5 kilometer, and simulated maximum height at the base was up to 6. It can go up to 6 meters. So the 6 meter height that was there, that basically blocked the Saraswati river, and that is how that helped in, that aided in flooding of the Kedarnath town. The simulated maximum velocity we have calculated in case of debris flow 1 is 5 to 7 meter. This is how I told that we have to take our model from Himalaya to Deccan Trap Hills. So Deccan Trap Hills are also, there are some places very notorious for the landslides. Sahadri Hills especially. This is a village in Malin called Malin, very close to Pune city. In 2014, around in the wee hours in a monsoon night, the landslide happened from the basalt, weathered basalt material, and the whole village, you can see this edge of the village and that edge of the village. So in between lied my whole village, and that completely got wiped off. We have tried to run our model, and have successfully done it. We see that the material that was coming down because of the debris was sufficient enough to devastate this landslide, this village. You can see there is a list 4 image just before the landslide. This is the village This is the village. At this resolution, the village will look like this only. Houses, cluster of houses. And there is a spot image available in Google Earth. Anybody can see how the landslide looks like. So this is where the village light. This is another example from Kaliasol landslide that's close to Srinagar in Garhwal Himalaya. Yeah. Geologically, it is mainly quartzite. There are different varieties of quartzite, along with some schist bands, the material available there. And we tried to model it using debris flow and another, that is rock fall module. So this is my rock fall module, and the previous one was debris flow module. So what I do, I think the source area, I concept the source area as from the source, the maximum material is going to flow like a debris. In this case, we considered the material to flow like a rock fall module, in a rock fall mode. So we can see the material that is coming like this and getting accumulated here. Here also the material comes down, rock fall also, and then material gets accumulated here. The important part is this road. This is the road. There is a lifeline that caters to Kedarnath, Badrinath, all the city's shrines. So if this gets blocked, and for last few decades this is getting blocked in every monsoon almost. So that's how the important lies in modeling this. So in the next rainy season, suppose something happens, some more material is going to come down. How much material is going to come down, and what should be the preventive measures? We have tried to model this also. Okay, this is how to geologically assess the landslide as such. We try to get a rock mass rating value, how strong the rock mass is. Though it doesn't fall in the exact purview of this lecture, but just to make the viewers more comfortable, I have tried to give few measurements that can be postulated from these kind of studies to mitigate the landslide, big landslide like this. So rock mass rating will give you a particular value that basically helps you to tell what type of civil remedial measures can be implemented there. That will be sufficient to hold the material so that further activation of the landslide doesn't happen. This is what the Kaliasol landslide tells in detail. We have tried to model this. The successful model results I have seen. Additionally, we tried to think of some source, the causative factors behind occurrence of this. You can see these ABCD lines and this line. This is the road. This is the road. Now along all this, we have run our geophysical instrument just to check. We have run the resistivity instruments. Resistivity will tell obviously that whether down surface, under the surface, there are occurrences of water shoots or no. We found that some water shoots, hidden water shoots were there. That actually makes the condition more vulnerable, especially in the monsoon. This is how we validate the result. I have told you that in our models, in debris flow modeling, the two parameters apart from that we give from the DM or the satellite images, apart from that we give two geoengineering parameters, frictional parameters, mu and xi. So this mu and xi, whatever we have given that as input to the software, we got a successful result, we validated. We go to field, collect samples, and maintaining the same, almost the same saturation in the lab, we analyze the samples and try to see what is the mu and xi value that is coming from the samples analyzed instrumentally in the lab. Now, a landslide happened there. I have given an input mu and xi for my model and something that I have calculated from the sample collected, physical samples, and analyzed in the instrument. Now, both these will give me a set of mu and xis. So these frictional parameters from both the sources, they should be at par, they should be similar. If they are similar, then the model is validated. We have tried to do this exercise for all our debris flow and found that they are in the range. So cohesion and angle of interresistance, suppose here and here, they are almost similar. They are nothing but derivatives of mu and xi. So we have seen that they are almost similar values. I believe that is the end of this presentation. Just the conclusion is left. What we can conclude from this today's discussion: first part we have described about the hazard zonation. Second part we have learned how the models are to be prepared. Now, model height, momentum, and velocity of, in case of debris flow 1 in Kedarnath, as we have shown, they provide sufficient blockade to the main course of River Saraswati that changes course and consequently flooded the temple area. That is one major conclusion that has come from this kind of studies. The numerical simulation and flow modeling that we have done in the second part, that can be very critically, that can be used for calculation of vital physical parameters that help in real-time mitigation. Now, the shear strength parameter, that is the mu and xi values that a good model has to be provided with, can be validated by laboratory instrumentation techniques. So that is the bit we can validate it back. Future potential flows of a debris nearby to a already existing one can be modeled if my geology and topography, other factors are similar. So a future flow that if you think that, okay, the material is going to come down in next rainy season like this, we have to understand that landslide hazard zonation gives me a clear-cut idea about the land pieces, the pixels where the land is prone to maximum hazard, or where exactly it is. But at the same time, what does it tell to a villager? Suppose he is not that much educated. So to him, if you tell that, okay, this is very high vulnerable, very high susceptible area, it doesn't mean that much. It doesn't mean anything to him. But if you tell that the material, he has a house there, and behind his house lies a slope, and upslope lies a rock that is clinging and precariously clinging, and it may go down in the next rainy season. So that is a real threat to him. If we can model by using this kind of debris flow modeling, that if that material really gets lodged up and then it comes down under the influence of gravity and hits his house, with what velocity it will be coming down, at what height of the debris it will come down with. So to arrest this, at least we can make implant a dam, check dam kind of thing, wall kind of thing, so that it digests the initial thrust of that. So his house is safe for that time. So that is the beauty of this kind of simulations. And obviously change detection in case of repeated flows like big landslides, big debris flow that we have seen 3-4 examples here that happen every rainy season, every monsoon. So in case of repeated debris flow also, we can make a change detection kind of study. So this much of material that has dislodged of this monsoon, next monsoon I believe that this much of material is going to come down. If that comes down, so this will be the height, and this is how, if you implant a dam, that can be the flow will not affect at least my roads or the vulnerable locations, house, villages, etc. That is all. Thank you.